Hello, ladies and gentlemen. This is Dean from Awfully Pie, and this is linear algebra. Now that we've looked at transformations, we can talk about what happens when we look at a vector from two different perspectives. Let's say that we want to define a subspace of R3 by a basis B is equal to the set of V1, V2. And we've seen many times before that this is a plane in R3 any way that you look at it. However, if you were to orient R3 in a different way, such that you were to view the plane such that it had the basis C, which is the set of W1, W2, then this is what's called a change of basis. Keep in mind that we define V1, V2, W1, and W2 all in terms of an absolute basis, which here is the standard basis because we're in R3. A given vector x will have different coordinate vectors in each basis because they represent different standard unit matrices, which are matrices whose column vectors are the basis vectors of the subspace. And multiplying these matrices by x's coordinate vector, these hard brackets mean with respect to, would give x in terms of our absolute basis. If we want to translate a vector from one basis to another, we first need to think of a way to interpret C in terms of B. Fortunately, like I said, B and C are defined in terms of an absolute basis based on our objective point of view. And when I say objective, that's in the sense that it's independent of any given basis and is generally the standard basis. Viewing either basis in terms of itself would result in just the standard basis, and that isn't what we're looking for. And that's also not the case when looking at it from the other. So we look at it in the terms that they're given. Say we're looking to transform B to C. The convention is to list them backwards. It will make sense later. We are first going to look at B in terms of C, or the basis matrix B with each column a coordinate vector in terms of C. This represents a new matrix P, B to C, and in fact we could write B as B in terms of the standard basis, but this is trivial and almost like saying that x is equal to 1x. Now multiplying B by C, or B in terms of C, by x with respect to B will give x with respect to C. This is why we write it backwards, so that they seem to cancel out the touching sides. And this works both ways as well. So you can switch B and C as much as you want, or any other basis, in fact. You'll also find that B in terms of C is the inverse matrix of C in terms of B, always. For an example, let's look at if you had B is equal to the set of 2, 3, 4, and 3, 6, 9, and C is the set 1, 1, 1, and 1, 2, 3. If x in terms of B is 4, 3, let's find x in terms of C. First, you're going to look at the vectors in B and give them as coordinate vectors in C and make a matrix out of that. And then multiply it by x in terms of B, and you get 413. We can check this, like I said up here. If we multiply the matrix representing B by x in terms of B, you just get x, which will, in terms of the standard basis, is just 17, 30, 43. And doing it the same way with the C matrix and the C coordinate, it's the same, so it works. Now, sometimes you might see a question that looks like it asks for a transformation from a basis to itself. You might think that you'll end up with the identity matrix, but that's not correct. Obviously, looking at this like before, you would, so that wouldn't work. Instead, we're going to have to do this a bit more rigorously, and this is actually the way that the first way works, but a bit unshortened. First, given a transformation T and a basis set consisting of vectors, T, B to B, can be found by applying T to each vector in the basis B, then assigning a coordinate vector to that transformation with respect to B. in saying this, you can think of this as T of B with respect to B. This isn't a change of basis per se, but rather the matrix representation of a transformation that we talked about last episode, or the associated matrix. It might also be helpful to know that transformations and a change of basis can be applied even between them.